You're now going to perform an investigation to use a kettle to measure the specific heat of water. For this investigation, you're going to need a kettle. You'll need to be able to read the power that your kettle uses off the bottom. The bottom of this kettle says 2200 to 2400 watts. So I will use 2300 as the power of this kettle. If your kettle doesn't have the power on the bottom, you can assume that the power used is 2000 watts, but your results will be less accurate than if you read the actual power that your kettle uses. You're also going to need a measuring jug to measure the water in. And you will need a stopwatch. You may use a stopwatch, or you may want to use a stopwatch application on your iPhone or on your computer. So the physics behind what you're going to be doing is you're going to be using two equations. You're going to be using the equation that we've seen, Q is equal to mc delta T, which tells you how much heat you have to add to change the temperature of water. You're also going to be using the equation that power is equal to energy over time, or in this case, Q over time, the heat over time. So we will be equating these two equations so that we have P is equal to mc times the change in temperature over the time. You're going to be having the same change in temperature each time. The temperature of the water will be starting at room temperature, which you can measure if you've got a thermometer. If you do not have a thermometer, then assume that the room temperature around you is 25 degrees and that the water is in thermal equilibrium with the room temperature. So use water from the cold tap, not from the hot tap. The final temperature of the water is the temperature at which it boils, which is 100 degrees C. You'll be measuring the volume of your water in litres. So remember that 1 litre of water weighs 1 kilogram. So if you have, like here, 350 millilitres of water, then that is 350 grams or 0.350 kilograms. Now, there's several things you're going to have to do to conduct this experiment accurately and safely. It's very, very important that you conduct it safely. So before you fill up your kettle, make sure that none of your power cables are frayed, that it's all properly coated in an insulator and safe. You need to keep your work area dry. If you spill any water, turn off the power, mop everything up before you proceed with the experiment. Now you're also going to be dealing with water which can get very hot. So you need to be wary of the hot water. Pour it into the sink carefully. Try and keep your arm as far away from that hot water as you can, as it's emptied out of the kettle, lots of steam will be formed and steam can burn you as well as the water. So stand back and pour it down the sink. You need to agree to these safety restrictions before you start the experiment. Performing this experiment shouldn't be more dangerous than boiling water for a cup of tea, but you do need to be aware of all those safety concerns. Now we want to conduct this investigation as accurately as possible. So to conduct an accurate and reliable investigation, there's several things that we have to keep in mind. We need to keep as many of the variables constant as we can. So anything that we're not changing on purpose needs to be kept constant. So one thing that you will be varying is the volume of water. The variable that you will be measuring is the time it takes this water to boil. So those are the only two variables that we want to vary. We want all the other variables to remain constant. So variables such as the initial temperature of the water need to be kept constant. One way to keep the initial temperature of the water constant is to perform this investigation in one day. If it's all performed in the same day, then we can assume that the surrounding temperature isn't changing very much, and so the water is coming out of the tap all at the same temperature. So just keep in mind that you want to keep all the other variables constant apart from your volume of water and the time it takes to boil. Now, the other thing that we need to do to have an accurate and reliable experiment is to repeat the collection of results. And for that reason, for each volume of water, you're going to boil the kettle 3 times. You'll record the time it takes to boil with that same volume 3 times, record that in your table, and this also gives you a way to estimate the uncertainties in the time it takes to boil the liquid. Now, we also need to consider uncertainties whenever we're doing an investigation. It doesn't make much sense in science to say, well, the result is that C is equal to 4,100 joules per kilogram per Kelvin, without telling the person who's reading our report how certain we are that that is the correct answer. In this experiment, you will have relatively large uncertainties. So I recommend that you deal with the uncertainties. You do have the option of just ignoring the uncertainties, which will result in a slightly lower mark. But if you're just finding it too hard to deal with the uncertainties, you may want to just skip them this time. So how you calculate the uncertainty is in the volume is estimate how accurately can you measure the volume using your measuring cylinder. In this case, the measuring cylinder only has markings every 50 millilitres. So I would find it hard to measure the level of water in here more accurately than, say, around about 25 millilitres. We usually do about half the smallest increment, but you can estimate how accurately you think you know the volume of your liquid. If you have accurate scales at home, you may want to weigh your water instead of using the measuring cylinder. That may give you a more accurate result. So before you start this experiment, you should write up a table to fill out with all your times as you go. You want to record these as you go. So now you're ready to start. You'll need to put the water into the kettle, do this for 5 different volumes and repeat it 3 times for each of those volumes. Once you've got all your data in the table, you're ready to analyse it. Now, to analyse it, we're going to draw a straight line graph. We draw a straight line graph because this effectively takes the approximation of all our measurements and gives us a much more accurate answer. Now, there are straight line graph templates that you can download from Moodle if you want to. These are Excel templates, so you can just put your values in there. And in a minute, we'll have a look at how you might go about doing this. So enter all your values into some straight line graph template. You can use R1s or you can find another one on the internet. And from this straight line graph, you'll be reading off the gradient. Follow the instructions provided to calculate the specific heat of water using these measurements. So the accepted value for the specific heat of water is 4,186 joules per kilogram per Kelvin. This experiment is not going to be too accurate, but you wouldn't want to be off that answer by more than about 1,000. If you're off by more than about 1,000, I recommend that you carefully check your calculations. Let's have a look now at how you would go about doing this graph if you were to use the Excel templates provided.
When you open up the linear plot with errors template, it should look something like this. So what we want to do is on our x-axis, we want to plot the volume, which remember is also the mass of the water. So we'll plot the volume in litres, so that is the mass in kilograms as well. And on the y-axis, we want to plot the time, and we'll be plotting the time in seconds. Now, we'll need to enter our values in here. So I used 500 millilitres, 750 millilitres, then 1 litre, 1.25 litres, and 1.5 litres. You enter whatever volumes you used in there, and then we'll clear the rest of these cells. Now, the linear plot with errors is not going to work unless we enter the error in here. So the error, remember, is generally half the smallest increment. So when we were reading off the volumes there, we said 25 millilitres would be a reasonable error. So we enter that in litres, 0.025. And we have the same error for every one of those volumes, 0.025 litres. So this is only displaying my answers to 2 decimal places here. I can change that in the settings if I want. Even though it's only displaying it to 2 decimal places, it does know that there are 3 decimal places there, and it does take them all into account. Okay, now what I'm going to need to do is enter my times into this table. Now, to enter the time I should use is the average time for this volume of water. So when I measured how long it took to boil 500 millilitres of water, I got 1 minute and 20 seconds, 1 minute and 21 seconds, and 1 minute and 25 seconds. So on my calculator, I work out what the average of those is in seconds. 1 minute's got 60 seconds. So we want the average of 80 and 81 and 85 seconds, which gives us 82 seconds. Now to work out the error, what we need to do is use the range divided by 2, which is the biggest minus the smallest divided by 2. So my biggest value was 85, my smallest value was 80, so 85 minus 80 gives us 5, and then I divide that by 2, which gives me 2.5 seconds is the uncertainty there. I then repeat this for the other times as well. So I'll just enter those in now. Okay, now to get my final answer, I'm going to need to clear these last cells. So I go through and I delete these values. And so now you can see I've got a line of best fit, which is the blue line down the middle. It's then plotted 2 lines of worst fit. So the steepest and the shallowest lines that obey these relationships, that follow these trends. And so what it's done down here is give me the equations that describe these 2 lines. So the blue one is the line of best fit. So you can see this is the equation for a straight line, y is equal to mx plus b. And so this here is my gradient, 1.58, and this e means times 10, so this is times 10 to the 2. So let's now just have a look at how we would go about analysing this result. Okay, so I've got that my gradient is equal to 1.58 times 10 to the 2. So 10 to the power of 2 is 100, so this is 158. So now let's calculate the uncertainty in our gradient. To get the uncertainty in gradient, we need to do the steepest gradient, which is the highest gradient, which is this one here. So that is 169 minus the shallowest gradient, which is the 150 divided by 2. So I always do the biggest minus the smallest divided by 2 to get our uncertainty. When we do this for the gradients, we end up with 9.5. And so our gradient is equal to 158. 9.5 will round this up, plus or minus 10. And now the gradient is the rise over the run. On the y-axis, we put the time, and on the x-axis we put the volume. So the units for this are seconds over, the volume is in litres, or we can put kilograms. So seconds, kilograms to the -1. And now we're told that the gradient is equal to Cw times the change in temperature times the power. So for my kettle, the power was 2,300 watts. The change in temperature is the final temperature, which is 100 degrees Celsius minus 25 degrees Celsius, or whatever you measured the initial temperature to be. So this is 75. So we have that Cw is equal to 158 plus or minus 10 times this power, which is the 2,300, over the change in temperature, which is the 75. So we do this times 2,300 and divide it to 75 to both the value and the uncertainty. So this gives us 4,845 plus or minus 307, and this is joules per kilogram per Kelvin. And so if those were my values, this would be my answer for this case. Yours will be slightly different to this.